Hey everyone, this week's lecture will be on traditional object recognition. The current state of the art in object recognition is through deep learning. However, then we will devote the last 4 weeks of this course to that. However, today we will talk about traditional approaches, meaning pre-deep learning algorithms. We will go through the algorithm basics, which I believe will be important to understand the field, its evolution, and also important for various other applications. We will cover 2 different topics. First, specific object recognition. We will be looking to identify the same object in different images despite variations in pose and illumination. Then we will cover object category recognition, meaning we will look into identifying the object category despite variations in pose, illumination, and now this time intra-class variation. Let's start with the specific object recognition. We will first give the problem definition and then give various solutions, and at the end we will talk about how to make these solutions robust. The specific object recognition is probably best understood by contrasting it to category level recognition. Now, given an image, for example, the one given on the top left, our question is, in which of the other images does this object is present? For instance, I can see that in these 6 images, I see that the same object is present in this image and this image. In these 3 images, I can see that there are cars, but these cars are different than the one that I'm searching for. So they're in the same category, but they're not the same. In that sense, for specific object recognition, the car that I'm querying for is present in these 2 images and is not present in the other images. So a specific object means an instance of an object class. So the question we're interested in is, for instance, does my car exist in this image? While the related question in object category recognition would be, does a car exist in this image? So we're looking for the first one. Does my car exist in this image? Obviously, the applications for this goes beyond the simple toy example we've seen. For example, one pretty interesting application is searching photos on the web for particular places. Given the landmarks that we see here, for example, the Bridges of Sai or the Bodleian Library, we might be interested in pulling all possible pictures from the web that contains pictures of these structures, for example, to do a photo album or even to create a 3D structure of the image, assuming that different photos on the web will be taken from different angles. And this, through specific object recognition, can be done. It's called a large-scale retrieval, where I'm able to actually locate the same object in various photographs in the images. Now, this actually has pretty cool applications, and one of them was created in the Vision Lab here at ETH. You can imagine, for example, going through a city where you have an apparatus like the one that that lady is wearing in the image. And you might be going through the city, and the apparatus basically shows different landmarks that you see, and basically explains what they are and tells you their history. So in a sense, it's a very nice tool for mobile tourist guiding. Of course, you would need self-localization, but the essential part is the object landmark recognition. Actually, there's one application that maybe you're familiar with as well, which is called the Vivino, so one label recognition. There, the problem is exactly the same. Given the image of a wine bottle, you want to recognize the wine and tell the user its quality or metrics about the wine. And this was created in the lab here at ETH and was later actually sold. And now I think you can download the app and use it in your daily life. In the specific object recognition, there are 4 different challenges. And we've talked about these challenges when we talked about feature extraction. These challenges are, we want to be able to recognize objects despite variations in pose or viewpoint, despite clutter, despite illumination variation, and occlusion, as seen here. So we've already seen these to some extent. Now, how to do this recognition? There are really 3 main approaches: the model-based, the image or appearance-based, and hybrid model-based approaches. And we will talk briefly about all of them. In all the approaches, the underlying principle is the same. We want to convert the image into a representation. Here, for instance, a numerical representation. And then we want to compare the numerical representation, like the one shown here, with the representations of the images we have in our database. In other words, through our training images. Let's start our discussion with the oldest application, oldest approach to solving specific object recognition, which is the model-based approach. And there we will be constructing local geometric features. The first approach that comes to mind is really, given an image database, like the ones that you see here, we create structural models of the object that we want to recognize. So what does that mean? Structural models are really qualitative structural features. For instance, you can say that this contains two holes that are circular and four corners, and the two holes are captured in a square. This one has again two holes. However, these two holes are encapsulated by a larger circle. And these models are created by the expert, basically, or by the designer by hand. So hence they're called model-based approaches. In their applications, the idea is actually quite simple. We will assume that these objects may be present in any form or any pose in the image. So, given the object, we will basically try out different poses and compare it with the given image and to see if there's a match. So the representation is in a sense very geometric. So we are representing local geometric features, for example, circles, corners, and so on. And in most of these previous applications, the models are largely contour-based. So I have an object, I extract a contour of it, and I try to represent the contour with geometric primitives. Now, you can imagine that if I have these objects in my database, and if I try every possible pose and compare it with the images, this is a slow process. I'm first hypothesizing the pose of the object, and then I'm verifying with the given image. If I have a very large number of images in my database, you can imagine that this search can be quite slow. Now, in 2D, I can use geometric primitives, and in 3D, I can simply use the wireframe models. For example, if I have the wireframe models for a tool like this, I can use it, and through in the hypothesizing step, I can simply create different 2D projections of this 3D wireframe and compare the projected contour with the image that I have. Once there is a match, I can say that this object is present. If it's not, then I go through the database looking at the other objects. Now, the early attempts are really looking at the contours, and it dates back to 60s. Now, a little bit more recent, in the 80s, researchers were able to make these pretty robust to occlusions as well. In the next step of the evolution, researchers solved the problem of hypothesizing and verifying, which was a slow process, as I said. So instead, what they figured out is, given a contour of an object, I can perhaps extract features that are invariant to various geometric transformations. So the crucial advantage is, these invariants, they decouple the object type from the pose. So instead of looking at the object and trying every possible transformation, every possible pose, I can simply just extract these invariant features and compare them with those in the database. So I would only be searching through the types of objects. Now here, examples here can be given for completely visible planar shapes. So I want to be able to, for instance, create features that I can extract from this contour that are invariant to affine transformations. And this actually can be achieved by simply creating signatures of the outlines of these images. So, in a summary, I want to create invariants that I would extract from this picture here and this picture here, which is, for example, my database. And because the features are invariant to transformations, I will be directly able to compare them with those in the database and say that this is the shadow of a swan. Now, we can actually talk about multiple examples in this respect, but just to give you one example here, you can create such invariant features by looking at geometric signatures that are invariant to affine distortions. For example, one of them is given here, and another one is given here. Now, we don't have to go into details of what they are. If you're interested, you can look them up. But the essence is, if I actually think about this as a function of this one, then I will basically get a signature that is unique for every contour and despite the affine transformation. Believe it or not, these two different shapes will have exactly the same signature, and that will be able, I will be able to compare it. Now, using this, people were able to create features that are invariant to projective geometries, projective transformations, and were really able to recognize objects in complicated scenes like these, again using contour-based, model-based approaches. So the model-based approaches have good mathematical properties. I can either try multiple poses or I can extract invariant features. And they're useful in industrial applications where I have full control of the setting and the lighting. However, the user needs to define a structural model, and this is a little bit complicated. We didn't go into the details of what a structural model is, partly because sorry about that, and partly because it was a little vague to define. So their use in general object recognition is rather limited. Next, we will talk about another approach that actually came afterwards, and that's image-based methods or appearance-based methods, which has a larger use case. So in the image-based approach for specific object recognition, we will actually try to create global representations of the image. Now, the simplest example of image-based or appearance-based method is actually template matching. So the idea is rather simple. If I want to look at this object, or if I want to identify whether this object is present in the image or not, I can simply use the image of that object as the template. So I can actually take this template, I can shift the template over the image in a sliding window approach, and simply compute the normalized cross correlation or sum of squared differences between the template and the image at the position where it's overlapping. Now, if I do this, for instance, I can see that actually the highest point of normalized cross correlation between the template and the image will really be at the location where I can see the image. So that's pretty neat. And here notice that I do not use any model. I directly use the image. So it's quite simple. I don't have to create anything. The problem is, if I have lots of objects in my database, then the number of templates that I need to create increases. That means if I want to search, for example, 15 objects, then I need to compute the normalized cross correlation or sum of squared differences across an image using 15 different templates. Now notice that I use the image of a template. That means that I only have one pose of this image. So in order to gain any robustness towards pose or illumination changes, I need to increase the number of templates. So the problem becomes really huge. If I include the variation in the appearance because of changing the viewpoint and lighting, now even for a small number of objects, I just don't need just a number of object templates, but I need a lot of templates. So this becomes rather very difficult in practice because that means that for each template, I need to recognize each object, I need to run many different template matching searches. Fortunately, this can be actually improved by using principal component analysis. So we covered principal component analysis 2 weeks ago, and I believe you've seen applications of PCA for texture analysis last week. Just to remind, PCA represents data samples in a lower dimensional space by keeping most of the variance in the components. It was seen to be powerful for similar patterns like faces, which exhibit a lot of redundancy. So mathematically, I have the image I, and the image I was simply represented by mean plus the principal components and factors that are unique to the image that I can use with the principal components to reconstruct the image. So in a sense, I can represent the image simply by looking at its principal components. Now, the PCA weights are wonderful global image representations, and they have been used for object recognition, in particular specific object recognition, in practice. And notice that I don't really need to have different template for each variation. Instead, I can actually try to create PCA models to capture the model variations due to pose and illumination changes. So let's see how this is done in one example. The earliest paper that looked into this is by Nayar et al., and it was looked at 1996. So for training or creating a database, for every object that I was interested in, you simply sample the set of viewing conditions, mainly viewpoints in this example, but it can also include illumination. Using these images as feature vectors, after manually bounding boxing, fitting around the object and rescaling brightness and normalization, you apply a PCA over all the images. And this includes mainly viewpoints, different objects all together. And then you keep the dominant principal components as we've seen. And in Nayar et al.'s approach, even 10 or 20 principal components were already enough. Sequence of views for one object then are used to create a manifold in the space of projections. And this manifold was actually created by simply placing the representation of these images in the lower dimensional PCA space, and then simply fitting a spline to it, and then density sampling if desired. So during recognition, we basically take the image, we convert it into the principal components, and we try to find the nearest manifold to the test image. So let's talk a little bit in detail how this is constructed. In Nayar et al.'s approach, they basically put the images on a turntable and imaged from a fixed distance under a fixed elevation angle. And then they turned the turntable and took many different images. So these pose changes were, in a sense, limited to changing in the azimuth angle, but you can imagine that actually you can do a lot more in the same approach. Then you take all the images for the same subject and project them into the principal component. And in this case, for the illustration, we're showing it everything 3D so we can see it, but you can imagine the splines can be fit in higher dimensions. So you put all the images of the same object in the principal components and simply fit a spline between the different points to get a much denser manifold of the object appearance. And this actually creates a sufficient characterization for recognition and pose estimation. So let's look at how this looks. As I'm turning the turntable and looking at the object in different poses, I'm following where it lands in the principal component space. You see that in the principal component space, the image actually follows very nicely the spline representations that I created for this object. Now here I only show the manifold or the spline representation for one object, but you can imagine in the same space we have multiple of these manifolds that are constructed for the different objects. So for when a new image comes in, I simply find a point in this space that corresponds to the image by basically applying the principal component analysis on that image or converting it to principal components. And then find the closed manifold to that point and say that and conclude that the image that I see is coming from the object that created that manifold. So let's see this in an example. Here what I show is, okay, my mouse to work again. Okay. Here I have a real-time system. So I have one object and I simply now look at use the system, and the system is able to find first what object this is within the data set that I have, and furthermore identify the pose of the object based on where it lands on the manifold that was created by that object. And the nice thing is, if you have an object that is not in the system, it will fall so far apart from all the other objects that you can actually create a threshold on the distance to the closest manifold and say that if it's higher than a certain distance, we can conclude that you have not seen this object in your database. Now, such objects were actually the principal or the initial approaches, where PCA and the global image representation found their biggest application was the eigenfaces, or the face recognition systems. Now, we've already delved a little bit on this topic in the past 2 weeks ago, where we talked about how PCA was applied to face recognition in the very earliest works. And those were the initial works, and a lot of extensions have been done over them to create 3D representations of shapes using PCA models. Now you can imagine the shape of a face in two distinct aspects. One of them is the actual geometry, the morphology of the object. And you can actually create a PCA model that represents the morphology. So you can create the eigencomponents and the first variations and so on using the morphology. You can also look at how actually the texture or the illumination and the color changes on the face as well. And you can actually create another PCA model for changes in the texture and in the color of the skin. And using these two different PCAs together, you can actually create systems to recognize images, face images, in these 3D scans. Now, let's do a slight diversion and play a little bit further with the PCA model that was used for face recognition or face construction. So first, let's look at how the modes differ in these images. Sorry. So in the video on the left, what I show you is the principal modes or principal components of the face space that I created using the eigenfaces. So we've seen how the morphology changes, and now we're seeing how the PCA over the texture and the skin color changes the image. On the right, what I do is I take images of certain individuals, I map them to the PCA space, and then I simply interpolate in between them. So in that sense, I create morphs between the images of different individuals. And notice that I cannot seem to create this. And notice that actually the PCA space is quite powerful in representing individual faces, but also what comes in between, the interpolations, look also rather realistic. So it's actually able to really cover a large span of variations of face shapes, skin color, and texture. Now, that example was shown for 3D. However, you can actually construct systems that are able to recognize 2D images as well. Well, in order to be able to do it, the first part is a 3D reconstruction. So in the slight diversion, we'll see how the PCA actually can be used, the 3D PCA of faces can be used to reconstruct 2D images. For example, we can actually reconstruct the face here in this image from the self-portrait, or arguably self-portrait, of the young Anthony van Dyck. We can basically now look at the 3D PCA and create objects or 3D representations and create projections of the 3D representations and find the one that matches the 2D projection that we see in the image that we observed. Now, this way, notice that I can actually use the 3D face PCA to recognize 2D images by basically finding the 3D PCA components plus the pose or the projection. So in a sense, this actually goes back to the first model-based approaches and combines the image-based and the model-based approaches together. I basically first hypothesize an appearance, and then I basically hypothesize a projection angle, and then I look at the different PCA components with the correct projection angle to find out which one fits best to the image. Then I can do recognition based on the PCA components that I've seen. Now, a small comparison between the model-based and the appearance-based techniques for specific object recognition. The pure model-based techniques were actually quite compact, and the later techniques, not the initial ones in the 60s, but the 80s and the 90s, researchers were able to develop algorithms that can deal with clutter and occlusion. The issue were the algorithms were very slow because it has to hypothesize and then verify, or analyze by synthesis approach was rather slow. Creation of the models were rather difficult because either you create very detailed qualitative models or you have to find these invariants based on the contours. And its applications were limited to certain object classes and also on images where the contours are really clearly or can be clearly identified. On the other hand, the pure appearance-based models were very efficient because I was able to really find the principal, especially using the principal component analysis, they became very efficient in creating. So I can actually just have the images and build a PCA model just looking at the images. So models were easy to produce. The matching was efficient because I simply, when a new image comes in, I simply project the new image to the principal components and look at the components, compare a few numbers with those in the database, and identify which fits the best. And I could actually apply it to a wider class of objects because the models were easy to produce. I only needed images for them. The issue is the models actually could be large, especially when I talk about variations in viewpoints and illumination. On the other hand, it's not very easy to deal with clutter because the PCA components or the templates actually need to see the entire image. So if they're cluttered, that means the components will change dramatically and the matching step might not work.